Hello, good morning, good afternoon, good evening, everybody, wherever you might be. It is my great pleasure to welcome ARUP KUMAR from the Indian Statistical Institute from Delhi. And he will tell us today about, it will be a crystal clear talk about the crystallization of the C-star algebra of SUQ n+1. The Zoom is yours, take it away.
Thank you, Peter, for the opportunity to speak here. So here is an outline of what I'm going to plan to discuss today. I'll start with a few words on what led us to the study of crystal limits, or rather the hunt for crystal limits of the sister algebras associated with the Q deformations of classical groups. So it goes back to this paper by Kohn on local index theorem and so on SUQ2. So he studied this spectral triple for SUQ2. Now, the problem with this spectral triple is that it lives on the L2 space of SUQ2, which is basically the GNS space for the Haas state of SUQ2. Now, the L2 space, the orthonormal basis there is indexed by half non-negative integers, and one problem is that the action of the generating elements or the sister algebra elements on this space, they're not so simple looking. So it's kind of difficult to do computation. So the generating elements alpha and beta, for example, these are like combination of weighted shifts, and the shifts for the two operators, they go in different directions and so on. So what Kohn observed was, the crucial observation was that if one goes to the case Q equal to 0, immediately things get simplified a great deal. So at Q equal to 0, that complicated looking operator earlier becomes just a simple shift. And same for the other operator. And also you observe that if you take the relations for CSUQ2 and you simply replace Q by 0 there, you get a set of relations that gives you a sister algebra. And this gives a representation of that sister algebra. And using this, basically he could exploit this a great deal, and he used this to prove regularity and so on. So followed by this, there were a host of others who took this idea and used it to study other spectral triples, whatever was available at that time. And there were very few actually equivariant triples available at that point of time. So these are the ones that I can recall. Now, a few years later, Nezhviev and Toussaint came up with a equivariant Dirac operator for a much larger class of quantum groups, namely the Q deformation of all simply connected compact Lie groups, which basically covers, all classical Lie groups, a compact form of all of them. But on this side, there is a big vacuum, kind of. Other than a paper by Nezhviev and Toussaint again, where they prove something, a result on K homology class of their Dirac operator. I don't think there has been anything on this Dirac operator, the Dirac operator, on any of the other groups. Now, when we tried to look at this Dirac operator, so what we thought was that maybe looking at the Q equal to 0 case may help, because basically the idea is to understand this better. And somehow that L2 space, again, as operators, those are not very well understood, at least that's to us. So we wanted to see whether looking at Q equal to 0 could help. So we looked at Korn's paper again and tried to see what is happening there at the C-star algebra level when one goes to Q equal to 0. So what we observed is the following. So L2 of SUQ2, as I mentioned earlier, so the L2 space, the orthonormal basis has a natural indexing by this, n belonging to half integers and ij belonging to minus n to n. So there is a unitary from this space, small L2 of this, to L2n tensor h pi. H pi is this space where CSUQ2 has a faithful representation. This I'll come to later in the talk in more detail. So there is a unitary from this to this you can call multiplicity space, this tensor with h pi, so that for all Q, what you have is not unitary equivalence, but an approximate unitary equivalence. So the difference lies in Toeplitz in the first copy and compact in this part. And also the same unitary actually transfers the equivariant Dirac to a Dirac operator that had already been studied for this representation. So, so this is the connection that that we observed. And the point here is that this unitary, normally it would be very difficult to come up with this unitary, but when you go to the Q equal to 0 case and look at the representation of CSU 0, 2, then the unitary becomes somewhat natural, somewhat in the sense that you look at the lattices that you have on both sides, and then it's kind of easier to obtain. And that same unitary, which gives you a perfect unitary equivalence in the 0 case, that unitary works for all other cases and gives an approximate unitary equivalence. So,
sorry, Arup, just a stupid question.
Yeah.
The S in your formula for pi q is just the unilateral shift, right?
Yeah, right.
Okay.
So here, this S is left shift. And here, of course, it does not matter. On Z, it is left shift again, but here it's, yeah. Again, I'll introduce all of them later on when I come to the sister algebra SUQ n+1. Yeah, so going to SUQ3 case, the first hurdle, immediate hurdle was that how to make sense of the sister algebra at Q equal to 0. So in the SUQ2 case, it's kind of straightforward. You just look at the relations, you put Q equal to 0 there, like in the earlier slide, and you get a sister algebra which you call the sister algebra at Q equal to 0, and you work with those. But for SUQ3 or the higher SUQNs, you can't do that. It's not clear what should be the limiting sister algebra, and then also you need to know its representations if such a scheme is going to work there. So that is what led us to the crystal limit. That is what would be the crystal limit for the higher rank groups. Okay, so next let me introduce the sister algebra SUQ n+1 and its representation. Also, while doing that, I'll go over some of the other objects associated with Q deformation of these groups. So the setup is going to be the following. For us, of course, K is going to be SU n+1. And G is going to be SL n+1 C. But let's keep the setup more general, because eventually you would like to do the same thing for other types also. So associated with this K and G, there are two classes of objects at the quantum level. So one, quantized universal enveloping algebras. So UQG comes with a hop structure, and also it has a star structure corresponding to subgroups whose complexification gives you this. And on the other side, you have quantized function algebras, where you have coordinate function algebra of G, which has a hop structure, and then you have different star structures corresponding to different real forms of the group G. When the star structure corresponds to the compact real form, then the notation, so that is why I've denoted used K here. So it means we're talking about the star structure corresponding to the compact real form. And then, of course, you have the sister algebra associated with that.
And here your sister algebra is unital, right?
Unital, because we are looking at compact.
Yeah. So that basically you can call it compact quantum group sister algebra. Okay. Okay.
Yeah. Okay. So now let's go over some of these. So quantized universal enveloping algebra. So in the literature, there are these three types of quantizations that are there. One is this algebra over power series ring, UHG. This is Greenfield deformation. The second one is a kind of rational form of it. So this is defined over the field of rational functions. And the third, which is for non-zero complex values of Q, UQG, Q deformation of the universal enveloping algebra of G. So we are going to be primarily interested in this, but also we'll have to keep an eye on this, because we'll need this also. For this talk, we are going to ignore the first one. Okay, so the Lie algebra G, so it's given by these relations, and universal UG is just the associative algebra given by the same set of relations. So let's come to the next one, right? UTG. So UTG, the quantized universal enveloping algebra over CT. So this is defined, this is an algebra over CT. So this is given by these relations. So here Aij is the Cartan matrix associated with this particular G.
Wait. So CT is what ring? Because I want to make sure I understand the notation.
Right, rational functions. So,
rational functions, okay. Okay.
Right.
Thank you.
So here Aij is a Cartan matrix associated with G, and this is the symmetrizer of Aij. So in our case, as we are looking at the type AN case, these are all ones. And this is an integer matrix where the off-diagonal entries are non-positive. Okay, and UQG is again given by the exact same relations, except that you replace T by Q here, and Q here is a here Q is a non-zero complex number and not a root of unity, but eventually we are going to be interested in the case Q be real. So just to keep things simple, we'll restrict ourselves to Q between 0 and 1.
In your last equation, last two equations, the QI is Q, right?
Sorry?
In your the last two, the cell relations, the quantum version, the Q polynomial should be Q instead of QI, right? So what is
okay,
this
sorry.
QI?
No,
Yes.
I did not. So this is Q to the power di.
Okay.
So this is QI actually. Normal
Okay.
notation for this is
Oh,
QI.
I see. Okay.
Here, of course, again, in our case, in this particular case, the DIs would kind of.
Is it the same with the TI in the previous slide?
Yes, same
Yes, yes.
Okay. Yes. Thank you.
here. This is not copy paste, so I forgot to change at some places. Sorry about that.
Yeah, no,
Okay,
no worries.
so this is UQ. Okay, now the thing is that this for different values of Q, these UQGs can be looked upon as a specialization of this UTG. So UTG is one single object defined over this field of rational functions, whereas this UQG for different values of Q, they are different objects. For each Q, you have a different object. And one can view these UQGs as specializations of different specializations of UTG in the following sense. So you take in CT, you take A to be the subring of Laura polynomials with integer coefficients. Now, then what you have here is what is called an A form. So this is a subalgebra of UT. Such that this gives you the entire UT. So I'm omitting G here. And now this A, you can make A act on C by evaluation. So A is this Laura polynomial ring. So you send T to Q. That allows you to make A act on C. So using that, you form UTA.
Then it just becomes a number and multiplies whatever is in UTA.
Right, and this is what you get. So there is such a subspace sitting here, for which you have this. So in this sense, UQs are specializations of UT. Okay. And now we come to the quantized function algebra. So the algebra of coordinate functions. So you take UT, you look at the finite dimensional representations of UT, you look at the matrix entries. So they constitute what is called the algebra of coordinate functions of G. So this is a subset of the dual. And similarly for UQ, you have exact same thing here, which gives you OQG. Okay. So they come with a hop structure. This okay. So this is the hop structure on UQG. So from the hop structure and algebra structure, you get algebra structure and hop structure on the dual side via these relations. So the right hand side is the quantized universal enveloping algebra side, and the left hand side is the quantized function algebra side. So you get algebra structure and hop structure from the quantized universal enveloping algebras through these relations, through these equalities. Okay.
Just a stupid question. I presume that the antipode is bijective. So what would be the formula for the inverse? Of course, on Ki is obvious, but what is S inverse of Xi?
Sorry, what is?
No, I see it. Sorry. No. I was wondering about the inverse for S. No, I see it. I see it. Okay. Sorry. I withdraw my question. I answered it myself. I I wanted to know the inverse of the antipode S, but it's obvious. Sorry.
Okay. So next. So for our case, for the SL like SUN plus 1C, where so here the G concerned is SLN plus 1C. The algebra of coordinate functions is going to be given by these relations. So I'm just straight away jumping to the description of this. So this is the so-called quantum determinant. And this condition comes from the fact that we are looking at the Q deformation of this group, SL group. And just to point out something here about the relations. So what they say, because these relations we will be using it at a later point. So here IJ and IL. And for the second one, you have IJ here, AJ here.
And sorry, what is length?
It's length.
Sorry?
Length.
Yes, but isn't just the sign
Sorry?
permutation, or is it something different?
No. This one.
Yes.
This is the length of the permutation.
Yes, but is it the same, just the sign of a permutation, or is it something different?
No. Length. So if you write it as a, so using the transpositions, you write it as a reduced word.
But
it's not sign, it's a number.
Minimal number of transpositions you need to get your permutation.
It's not just the parity of the number, but the number.
Okay, I see. So in the classical case, you have -1, so this number, in fact, only the parity counts. But
Exactly. Yes, Adam, yes.
Thank you.
The third one is when the two elements are these two vertices of a rectangle, then they commute. And the fourth one is about TIJs, when TIJ and TKL are these two vertices of a rectangle. So this will come up later once more. Okay, now comes the star structure. So this is the star structure corresponding to the compact real form. And from there, you get a star structure on the coordinate function algebra, and which makes it. So this is the notation that we are going to use. So in this case, the star structure gives us this additional relation. So this is the algebra of coordinate functions for the quantum SUN+1 group. And of course, you have the enveloping sister algebra of this that gives you the algebra of continuous functions, sister algebra of continuous functions on this group. Okay. So here are just 3 more relations which are useful. That's why I've displayed it separately, but these can be derived from the earlier relations. The earlier set is the one that we'll go with. Okay. Now we come to the representations of the sister algebra CSUQ n+1. So for that, first, so these are representations of the SUQ2 group. This is CSUQ2, which is very well known. So on L2N, you have TI is going to this. So these, yes. Okay. So basically, there are 2 families of representation. So here is one infinite dimensional one. And if you put okay, so this is one infinite dimensional one, and here is a whole family of one-dimensional ones. So using these 2, actually, you can form a whole family of infinite dimensional representations, irreducible, indexed by, again, the torus elements. But we'll look at, so using these, we'll form representations of SUQ n+1. So, like in the classical case, SUQ2 can be viewed as a subgroup of SUQ n+1, and there are several copies. So if we fix a K, this map gives you a sister homomorphism onto CSUQ2, and which commutes with the co-multiplication maps. So basically, this is what makes SUQ2 a subgroup of SUQ n+1 quantum subgroup. Now, this homomorphism you can use and then compose it with representation of CSUQ2 to get a representation of CSUQ n+1. So that is where these are going to be used. So for a fixed K, you use this homomorphism and then you compose it with the earlier infinite dimensional representation that we saw and the one-dimensional ones. So you get one-dimensional representations, which we're going to denote by this, and also an infinite dimensional one. This time it is dependent on K, which K+1th block. So that to keep track of that, we use K here, and SK we use for a certain reason that we'll come to in a moment. Okay, now using these, you can form more complicated representations, which you can do basically in whenever you have this co-multiplication map available. So you first apply co-multiplication map, and then you apply on each copy, you apply these representations. So you can form convolution product of representations. And similarly, now the reason used SK, the transposition, rather than just K, is because of this. Then we associate this representation with a word in the permutation group, which happens to be the while group for this particular group. So for a word, you can associate a representation. And then you can take convolution product of this one-dimensional representation with a representation here. So this is going to be the notation for this. Okay, now to help us visualize these representations better and to be able to work with them, I'll now introduce.
Sorry, can you remind me, please, what is psi? Pick up some SI1. Pick up one letter in your word. So what would be psi of this one letter?
Right. So I'm going to get into that because
you are going to explain it.
Almost like we are looking at symbols, so it's very difficult to keep track of things.
Okay.
So we'll try to do that with the help of diagrams next. So just a moment. I'm trying to copy. Yeah. Okay. So here, let's say we are looking at SUQ 4, SUQ 5 rather. So N is 4 here. So here you think of the straight lines going from the left to the right as representing the generating elements, Tij. So Tij is like going from I to J. So this, I did not put an arrow head, but basically these are all arrows going from the left to the right.
Okay.
So all these lines, they stand for the generating elements Tij. Okay. Now, when you apply psi sk, let's say psi s2. So what do you do there? So when you go to psi s2, what you do is
and what exactly is S2? What permutation is it?
2, 3, the transposition.
Okay,
so
2 and 3.
SI
Okay,
is,
transposition of I plus 1. Okay.
Right.
Yeah.
So when you apply psi s2, I think there's some Q missing, etc. But basically, this is that taking it to CSUQ2. So basically, you look at the 2, 3 block. So these goes to the corresponding generators for SUQ2. And all other Tijs, they go to delta Ij. That means the cross terms all disappear. So what you are left with are just these. Okay. And then you apply that representation of CSUQ2, which means basically this one is this operator. This one is this operator. This one is the left shift. This one is the right shift. And these other free horizontal lines, those are identities. So this is, if I go back to the previous slide, not previous. So this is this.
Okay.
Okay.
Mhm.
Okay. Now, what about convolution? So ultimately, what you are left with is okay. Let me. Sorry. So what you are left with is this this diagram. So where you have T11 is going to identity and so on. T445 going to identity and 2-3 block. So whenever you encounter such part of the diagram, this is always minus Qn+1. This is Qn, this is S, and this is S star. Okay. Now, next, what we want to see is what is the effect of taking convolution product. So here again, these stand for Tijs. So if you put one more here, now if you go from if you go from the leftmost side, let's say node 1 to node 3 here, all possible paths, that gives you delta T13. So T11 tensor T13, T12 tensor T23. So you can think of this as combination of all such things, right? Now, when you apply psi si here and psi sj here, what you get is something like this. So let me just make some space.
But when you apply coproduct to this T13, don't you get like the full sum from 1 to n?
Sorry? Right,
When
right,
you
right.
apply coproduct.
You get the full sum. So
Okay.
as I said, sum of all paths from the left side to the right side. So
Okay.
Like going towards the right. But when you apply these representations, then things get simplified.
Okay.
Let's say, okay. So let's say this is psi S2, and let's draw psi S3 here, which would mean that 1, 2, 3, you have this. Now their convolution product would be this. So now you can immediately see what would be the image of, let's say, T13. T13 would be 0. T43 would be combination of this, well, actually only this. So it would be identity tensor Qn. Okay, so convolution product means just putting the two diagrams together. Okay. Now comes the results that we actually need. So if you look at, okay, I have kind of not looked at those one-dimensional representations and convolution product with them. So maybe I'll come to that after these results. So if you take this psi q lambda omegas, so omega is a word in the permutation group. So it's basically convolution product of these psi SIs, and then you have the one-dimensional representation, which basically changes some scalars, but the Hilbert space does not change, and basically the operators do not change. So these give all inequivalent irreducible representations of this sister algebra. And so for different reduced words, you get inequivalent representations. And also, if you take the longest word in the permutation group, and then you integrate these representations over lambda, that gives you a faithful representation of the sister algebra. And that representation will act on. So this is the length of that longest element, and this kind of comes from the lambda part. And so we'll see how these representations look like in terms of those diagrams. Okay, so reduced word. So you can, if you follow this specific scheme, then you get a reduced word. So that is something that is well known. So basically, you take n1, n2, nk strictly increasing order, and then you have to take a kind of string of consecutive SIs. So here in this picture, for example, n1 is 5. So this string is S5, S4, S3, S2. So n1 is 5 here. N2 is 6, corresponds to this string. N3 is 7, corresponds to here. N4 is 9, and N5 is 10. So the point is, these should be consecutive. There can be some string missing altogether, but that's okay. But when you have something, they should be consecutive and they can stop anywhere. So if we follow this scheme, then we get a reduced word. I mean, there are other ways of writing reduced words, but we are going to follow this scheme of writing reduced words. Okay, and what would be the longest word? Longest word is when those n1, n2, n3 they cover all of 1, 2, 3 up to n. So this is like this is the longest word in this case. And now, what is the effect of that? Okay, I'll just go back briefly to that result slide. So this part, this lambda part, so the effect of this is the following. So here you have, so these are all copies of L2N, if you recall the diagram. So these are those individual psi k's put together while taking convolution product. Okay. So the effect of that lambda, what happens is you have so basically here you have copies of L2Z. There will be 5 copies here. Here it is 1 S shift, and the remaining ones are 1 identity. Then the next one, it would be S star, S, and then identity. Then A star is identity and so on. So that is the effect. So here you have 5 copies of L to Z, and here you have how many copies? I think 15 copies of L to N. So this is how that faithful representation in Sogelman's result that looks like. Okay. So now we have the sister algebra CUS associated with SUQ n+1, and we know what are its irreducible representations, and we also have this faithful representation. Okay. Now we come to the crystal limit. So sister algebra that we are going to associate with Q equal to 0. Okay. So here, first thing is a very simple observation. So if you go back to the SUQ2 case and the representation, so this was, so T12 goes to minus Q n+1, T11 goes to I hope I've written the S on the right side.
I'm a bit confused. Now we are talking just SUQ2, right? So what is this capital
Right,
N?
right. The capital N is like the Hilbert space is L to N. And this means the operator En going to Q to the power N En. So the capital N stands for the number operator.
But I still see no capital N on the right.
On the.
Well, you'll say that
No,
QN.
this is just a notation, right? So what I'm trying to say is you take the number operator.
Yeah, okay. So this is for you an operator, and this is just a number. Okay.
Right.
Okay. Yes. Sorry, this was confusing.
I'm sorry, I did not.
Yeah, thank you. I've got you.
Okay. I think I got the side. And incidentally, when I in the diagram, I think I mentioned S, so it really should have been this entire operator S together with this. So okay, so for SUQ2, T21 goes to Qn. So for this representation, the if you take Q0 limit, so these limits exist, first thing. And for T12, you can actually take out 1 power of Q and then take the limit, and you still, the limit exists because of this extra Q here, you can take 1 Q out and then take limit, and you still get something. So this is just a very simple observation in the SUQ2 case. So now when you go to the n case and you look at this representation, let's say, then so this basically translates to this, that this exists, and k plus 1 for this element, you can take a power of q out and take limit, and that would still exist. And this would actually translate to, now you can this limit would exist. Because what is happening here is in the kth copy, you have one going up and you have one extra q. So for other ij's, I less than j, it would automatically be true because this quantity would actually be 0. So only thing that is relevant here is really this one. So, but you have these two statements, like these two limits, existence of these two limits. And then
And formally speaking, you take this limit in what topology?
this is non-topology. This is non-topology.
No.
No. Okay. And now again another simple observation, but it's a crucial one, that suppose you have the following. So I less than j, and this is for all ij. Suppose these two limits exist for two representations. Then this would imply that the limit exists for no, not for all, for pi equal to pi1 convolution product pi2. Okay, you just have to keep track of the powers of q, and that would give you this. If these limits exist for pi1 and pi2, and the way the convolution product is formed, so you put those two diagrams together and then
it's clear. Yeah.
Right. And now, if you combine this with the result of Seuvelmann, what Seuvelmann tells us is that any irreducible representation you can produce as convolution of those psi SKs. And for psi SK, it's a trivial thing. So these limits would exist. So combining those two, what you will get is that these limits would exist for all irreducible representations. Okay, I have ignored kind of the lambda part, but that almost has no role in this. That does not contribute to the to these statements. So even when you convolve with those, it does not change anything. So what we have is now that for all irreducible representations, these limits exist. Okay. Now, one point here is the following. So I'm not so what I just now said is the following, that limit pi Tij exists for all irreducible pi, and also limit q to the power I minus j here in the second one, I is less than j here. Okay, so normally if I try to make this statement for a general element, it won't make sense, because when q changes, the sister algebra changes. So we can't really talk about an element in the sister algebra. But the point here is that these Tijs come from group theoretic consideration. So they are actually carrying more structure than just the sister algebra. So for each q, so these Tijs are matrix entries of one particular representation of UQG. So these can be made sense of, that is the thing. So while limit of pi a, this wouldn't have made sense, this is fine. So I'll come to this point again shortly when I discuss this other crystallization, Matasa and Yankin. So this point will come up there once more. Okay. So next thing what we do is the following. So you for each pi, you define, let's say, z pi ij to be the following limit. So we now combine these two in a single expression so that I don't have to write twice. So I'm introducing this minus sign for other reasons. Minimum 0 pi Tij. So this limit exists. So let's call this z pi ij. So these are operators sitting on the representation space of pi. Now you look at the relations that Tijs satisfy. Go back to those relations. A few commutation relations, then.
Sorry, I don't understand. What do you mean? What is written here?
So what we have seen is that these limits exist for each irreducible pi.
Yes.
Right? So this limiting operator, I'm just calling it z pi ij. So
fine, but I just cannot read what you wrote here.
Oh, okay. So this is minus q to the power I minus j, minimum and 0.
Minimum 0. So this or 0.
Right.
Okay. No, that's sorry. This was not clear.
No, fine. I'm sorry.
Yeah.
Okay. So you call this z pi ij, and then you notice that these z pi ijs, they satisfy the same set of relations for every irreducible. So, okay. And then, so what we do is we define the sister algebra at q equal to 0 to be the sister algebra given by those relations, and those relations are these. There are a few more which are coming in the next slide. Okay, so these are coming from the relations that Tij satisfied, and then looking at their images and then taking limit and keeping track of what is happening regarding Q. Okay, so now here again pictorially I'll just point out. So these first two are where you have Zij here and Zil here. So in this direction. The second one, again, the Zij here, Zkj here, one below the other, then you have 0. Okay. they commute whenever they are these two vertices of a rectangle. So these are essentially direct consequences of those. Okay, now what this says is that if the rectangle happens to be entirely on one side of the diagonal, I equal to j diagonal, or entirely below this diagonal, then this product will actually be 0. And the last two relations, they are about these two vertices of a rectangle, and what this says is that okay, basically let's say this is the diagonal. Okay, so if ij is anywhere here and kl is anywhere here, then you have this relation among them. So maximum of ij and minimum of kl should be separated by at least 2.
Okay.
Then you have commutation. So that leaves the case where they are separated by 1. So so if let's say ij is on this line, not in this part, just on these two lines, and kl just on these two lines. Okay, so when maximum of the ij's and minimum of the kls are separated by exactly 1, then you have this slightly more complicated relation. So their commutator is then given by the product of the other two vertices. Okay, and the quantum determinant condition that leads to this, the product being 1, and also the Tij star in terms of the minor, that gives this these expressions for Zij star. And here again, I'll just try to show what these actually mean pictorially. So let me draw a. It's not a good. Okay. So if Zij is here, if you take a Zii, then of course the star is, you just it skips that particular ii and it's a product of the other one. That is the first expression. So this is fine. If Zij happens to be below the diagonal, then what do you have? Then what you have is the following. So it comes via the diagonal up to here. If Zij is here, then it goes there and then again takes the diagonal. I'm not sure if I made it clear. So it is like this. It goes to the other side of the diagonal and then comes back to the diagonal. Similarly, if Zij is here, it comes via the diagonal, then takes this path.
Yeah, it's clear. Yes. Yes.
Okay. So now we just we define the sister algebra to be the sister algebra given by these relations. And again, you can ignore this. Let me skip to the next slide. And there, everything works out because one, the relations. So what you need is consistency of the relations, and then you need boundedness of the norms. And both those things follow. And in fact, another thing comes as a kind of for free is the following. You get a bunch of representations of this sister algebra coming from the representations of CSUQ n+1. You take any of those representations that we had defined, psi, whatever, lambda, omega, q. So this was a representation of CSUQ n+1 depending on some lambda in S1 to the power n and omega belonging to the permutation group. So if you take this limit and send your ijth generator to this, that gives you a representation of this limit sister algebra. So each representation of the sequence of this form, they will give rise to a representation of this sister algebra. Okay. So now, what happens in the other cases? So this is just the SUQN group that we have looked at. What happens for the other types? So, okay, we have not looked at all the other types, but and that's mainly because for the other types we have to write down all those representations ourselves. But for type C case, this was kind of readily available. So we had a look and things work out here also. So here representations are a little more complicated, but everything works out almost in a similar manner. So here, what varies are those elementary representations. So in our case, it was like in our diagram, the elementary representations were like this. In the type C case, there are two types of elementary representations. When it involves the middle one, it is like when it involves the middle two, then it's just one such cross, and then the operators are also a little bit different, but other than that, they share similar features. So the one going up has extra powers of q and so on. So you can basically make the same kind of thing work. So these representations were available here, so we could take a look, and basically things work out here also. Of course, the second part, what we do is representations of the sister algebra. There things would perhaps change. We have not looked at the representations of the limit sister algebra here. And I think for other types, it would probably work. The same thing should go through, but we have not looked at them. Okay. Now let's talk a little bit about this other crystallization that Matasa and Yamkin have given. So it's many ways it's similar, but there are some crucial differences. So again, let's look at the situation. So what we had was for the sister algebra, we had a representation. So what we did well was that we looked at irreducible representations on different Hilbert spaces, And we looked at only the generators and looked at what relations they satisfy on these Hilbert spaces. And looking at those relations, we constructed this algebra. So what they do is instead, they work with that faithful representation, again coming from Soy-Wellman's result. So
sorry, but I cannot read what you write. I mean, this one. What did you write here?
No, because I'm not being very careful. I'm sorry again. I wrote irreducible.
Irreducible. Okay.
Yeah.
Okay.
So in their case, what they do is they work with the faithful representation coming from Soy-Wellman's result. So the idea is that you, sorry, what happened? Touch something and went back. Just a moment. So what they do is basically they look at elements here for which this pi q a's will have a limit, and then collect together all those limits here and look at the sister algebra generated by those. Okay. But then problem would be that, again, you cannot really talk about without doing any extra work, because there is no A, because when you go to a Q prime, you have changed your sister algebra. So you are in a different place. So an element A that is available here is not available there possibly. So one has to make sense of that. So that is where they use the theory of crystal basis more explicitly. So just as UQG one could see as a specialization of UTG, using Kashiwara's result, it is possible to look at this not the CGQ, not the entire thing, but like the coordinate function algebra part here. It is possible to look at it as a specialization of part of the coordinate function algebra for OTG. And this is a single object defined over the rational field of rational functions. So using this, it is possible. So I'm not getting into the details. For that, one has to bring in more technicalities, and also one has to look at the exact results of Kashiwara there. So basically, the idea is that you write. So just like we have this Peter-Weyl decomposition, we have that here also. This breaks as a direct sum of chunks, and those chunks are basically highest representations. And it is here that Kashiwara has constructed crystal basis. So using those, you can make this work. So view these OQKs as specializations of this part of like OTG, something inside OTG. And then that conceptual problem that A is the elements A's are in different sister algebras, so you can't talk about limit. That problem can be avoided. So, and after that, what they do is basically you look at limits of operators here and define the sister algebra to be the one here generated by those limits. And so there are two good things coming out of their construction. One is that they're able to, by doing this, they're able to do this for all types at one go. And the other thing is, by relating it to the crystal basis and crystal graphs, they actually prove that this is a graph sister algebra, higher rank graph sister algebra, the limit. On the other hand, the way we have gone about it, that makes it possible for us to study its representations, which in this picture is not quite clear.
Sorry, but you touched the sensitive point. So a graph sister algebra is a limit of what exactly?
No, not graph. It's the other way. So what I'm saying is they have defined the crystal limit to be the C-star algebra sitting inside the carrier of that faithful representation. So the C-star subalgebra generated by limits of these operators. So you look at basically elements here for which these limits exist.
Yes.
Roughly speaking. And then you collect them together and look at the sister subalgebra that they generate. So that is the crystal limit.
Yes.
As per their definition.
Yes.
And in the process, they relate it to the crystal basis, as I said, mentioned, and crystal graph, and they're able to show that this is a higher rank graph sister algebra. Okay, and
sorry, I'm still confused. So what is this final step? How do you get a graph sister algebra?
No. I have not at all gone into how, because that's a long story, and I only understand part of it. I have not read the entire thing, the entire paper yet. So, but that's a there you have to bring in all the details of the crystal basis, etc., which is not what I wanted to do. I just wanted to mention what they're able to achieve by taking this approach.
Okay, I have one naive question. When you look at these rational functions in T and you apply this pi q tilde, what do you obtain? What kind of operators do you get?
No, okay, so it's like this. So you have in CGQ, you have so let's talk in terms of SU, let's say. So you have this coordinate function algebra sitting inside this sister algebra here. And in here you have OT, SLN plus 1C. Now there would be a part here, not the entire OT, but there would be a part here from which you have a map going to the coordinate function algebra here.
It's a commutative diagram. Okay.
And this is merely the composition of these two.
Okay. Yes. Sorry. Yes. Of course. Yeah.
Okay. So, in an ideal situation, of course, it will show that both the crystal limits give you the same sister algebra, and so that you, using their methods, you get that it's a higher rank graph sister algebra, and using, exploiting what we have done, you get that you get the irreducible representations and other representations, etc. But it's not clear yet whether we do get the same sister algebra or not. But that would be something interesting to see. Okay, so I'll quickly go over the representation. So this was one of the main things that we are interested in. Along with getting that crystal limit, we are also interested in its representations, irreducible representations, as well as anything more. Okay. So as I mentioned, so this way of defining this crystal limit that has this advantage. It comes, I mean, you get a bunch of representations for free. So you take this representation, you take this limit operator. So this representation acts on copies of L to N, number of copies being the length of this word. So there you take these limiting operators, you send your generating element to that operator, you get a representation. And that's by the very nature of the way you have defined things. Because these would satisfy the same set of relations, so you have a homomorphism, sister homomorphism, that's it. So each lambda in S1 to the power n and omega reduced word in Sn+1, we get a representation, just like CSU Qn+1 for Q non-zero. You have the same in each such Hilbert space. So for n equal to 2, we are able to show that these limits, they give a family of inequivalent irreducible representations. And in fact, this particular statement we can actually extend to n greater than 2 as well. So this holds for all n. Okay. I think I will skip the proof because I'll run out of time otherwise. Or maybe I'll come back to it in a moment. Let me just go and describe look at the other statement. This is the statement for n. So this is the same statement for n greater than 2. So those limits formed using those irreducible representations from Swavelman's result, that gives us irreducible inequivalent representations for the crystal limit. And then the other direction, that if we start from an irreducible representation, any irreducible representation must be of this form. So again, we are able to show this for n equal to 2. So here, basically, the proof proceeds in 2 stages. So you start with an irreducible representation. You want to show that it's going to be one of these. So the steps are the following. You identify this word, and then you try and show that it would be of this form for some lambda. And so here, to begin with, you don't have those diagrams, right? We don't know that the representation is actually of this form, but still the diagrams actually play a very important role in the proof. So basically, they tell you kind of how to approach the proof. So you try to extract various pieces of information, keeping the diagram in mind, and then you try and execute those. Yeah, I think I'll stop here because I do not really want to start getting into the proofs, because then I'll run over time. I'll stop here, but maybe I can answer if there are any questions and so on.
Okay, thank you very much. Before we go into more serious questions, let me ask you this. I know it was discussed during your students' talk, but I was quite distracted. So one more time, why is all that stuff called crystal? Where is this word crystal coming from?
That, I guess, comes from physics. I think it's at temperature 0. So somehow you equate that parameter to
Sorry, I didn't get it. What's your answer?
No, my answer is that it comes from physics, but I don't know enough physics to answer your question really, but it has to do with temperature.
Temperature. Okay, this is the word I did. Okay. Yes.
Right.
I had exactly the same feeling. Okay, I'm happy. I'm happy. Okay, Eric, good to see you again. What's your question? You have to unmute. Yes.
Yes. Thank you, Piotr. I actually would like to know if is it now only in this Matassa-Juncken case that there is still some duality with the Kashiwara result in the quantized universal enveloping algebra, or do you also still have some kind of duality between your a suitable subalgebra of your C-star algebra with the quantized universal enveloping algebra, but then at Q equals 0, and is there some nice duality with the Kashiwara crystal basis?
No, it's not duality as such. Okay, let me just go back to that slide. Right. So where they use Kashiwara's work is exactly here. So what Kashiwara does is the following. So you have, sorry.
So this is the Matassa-Juncken setup, right?
So I'll just draw a cleaner picture. So we have this coordinate function algebra for this compact group. And for this, we have this representations, representation, let's say, this is a faithful representation here. Now, corresponding to this, you have this OTG, right? Now, this is one single entity defined over this field of rational functions.
Mm-hmm.
So there is a subspace here which gets mapped to part of this. And it is exactly here that they use Kashiwara's work, because this OTG decomposes as direct sum of these blocks. And for each of those, Kashiwara constructed his crystal basis.
Yes, but all these bases in V lambda, where you have these crystal bases, they somehow come from a universal crystal basis in the quantized universal enveloping algebra, or Lustig calls them canonical bases.
Right. So this is a module, right? UTG module, let's say.
Yeah. So is there still some kind of duality, like you? So if you think of like SU2 in the algebraic sense, right? So you have generators for UQ SU2. You have generators for this dense subalgebra of matrix entries, and then there is some kind of nice duality between the two, which is Hopf algebra duality. Is there still some duality of this nature with respect to this crystal basis of Kashiwara on the one hand, and a suitable other set also on the other hand? And is it even a Hopf kind of algebra duality?
No. So Kashiwara basis is a slightly different object. So this is for modules over UTG. Okay. So first of all, you look for lattice here, kind of.
Yes.
So again, no.
Yeah. So that's an admissible
One
lattice.
moment. So here you have this V lambda. Okay. Now here you have what is called a crystal lattice. So for that, what you do is, so what is hanging around in the picture is also this CT, and inside this you have this algebra, which is now so for crystal basis it's now a different algebra. It's not the algebra of Laura polynomials, but it's
Yes, the algebra of specializable functions, right?
right. So now this one is this crystal lattice is something that is a submodule. I think this gives you the entire V lambda.
Yes.
And crystal basis is, and also, I mean, it has some extra properties. I'm not getting there because that involves defining the Cauchy-Euler operators and so on. L by TL, it's a subset from here, so it's not clear. I mean, like they are in duality with what, that part is not clear. I mean, I don't think I understand it well enough to
yes,
answer
I
you really.
don't understand it well enough. It's a kind of tricky business, all these crystal basis business. So thanks very much. Actually, I have another question, if that's okay.
Go ahead. Go ahead.
So you have all these irreducible representations of this Q. So this AN0. Is it actually clear that that the intersection of the kernel of all these representations is trivial?
Of the limit system algebra, you mean?
Yeah, so you have this AN0 C star algebra, and you have classified all the irreducible representations. So what is not so clear to me is the intersection of the kernel of all these irreducible representations. Is this trivial?
Yeah, it would be. I mean, if for a system algebra you have all the irreducibles, the kernel intersection of the kernels would be 0. Because any non-zero element, there would be an irreducible which carries it to something non-zero, right?
So, but you have so you don't look at it initially as a kind of algebra of generators and relations with a star structure, and then put a C star structure on it. So you already show.
Oh, you mean in the construction?
Yeah.
Just a moment. You mean here these relations?
Yes.
No. They're yeah. When you define the norm here, what you mean is whether there's a non-trivial kernel there and you need to quotient. Is that what you mean?
Exactly. Yes. Maybe you're right. I just don't see how it works.
No, here what we are doing is we are looking at the sister algebra given by these relations, right?
Yes.
So that is the standard construction. So you first show that these are consistent. That means you get a representation of the set of relations, which is fine, which will come as a limit of any representation I pick for the SUQ n+1s. That part is fine. And then you show that the norm that you want to define, that suprema over all representations, that would be finite for any element. And then you have to quotient, yes, but after that you get a sister algebra.
Yes. So the question
there, of
is,
course,
if the quotient will be trivial. So because if you have the quotient out with something non-trivial, it essentially means that your algebra is going to be smaller. So you probably have to add relations or whatever. So, and of course, we know that for SU, the quantum SU n+1, that this irreducible representation, the intersection of the kernel is trivial, right? So that all has been done. Actually, I did it a long time ago as well. And so there we know this, but you take the limit q to 0, and it's not so clear that in this limit q to 0, that this property survives. At least it's not clear to me.
No, so you are talking about, I mean, before forming the sister algebra then?
Yes, yes.
Because it's essentially a limit procedure, and it's not so clear that this property of having a trivial intersection of the kernels of these representations, if that actually survives in this limit procedure.
Actually, I'm not sure I'm getting your question right.
But maybe wouldn't it be strange that it's not 0, because it's like something constant. As long as q is non-zero, the intersection is 0, right?
Yes.
So then somehow, if you have a constant sequence equal to 0, it's hard to imagine that. But I agree, it's just hand waving.
Anyway, I enjoyed the talk very much.
Yeah, very good.
These were a few questions that came to mind.
Okay, anybody else?
Okay.
Tomek? Go ahead.
I have a question.
Yeah.
So if I remember well, these algebras, these limit algebras, are of type of higher rank graph system algebras. At least some of them.
No, I mean, for the one we have defined, we don't know. For Q non-zero,
you don't
yes.
know this. So
Q
during the talk
non-zero,
of your student, I asked this question, and you said that they are higher ranks.
So
no,
that is the one that that has been constructed by Matase Yankin, not us.
Aha. So it is not the same.
Right.
Okay. So
for the one
anyway.
For the one we have, yeah, this one we don't know yet.
Mm-hmm. So I'm asking this question because for higher rank graph system algebras, for some of them, there are some algorithms of computing K-theory. Does the knowledge of your representations help to compute K-theory of your limit algebras? And is it related somehow to this algorithm from graph system algebras? Or higher rank?
Okay, we have not looked at K-theory yet. Basically, as I mentioned, so our primary focus was on representations, and we are actually trying to get all the representation in the like higher end cases. For n equal to 2, we could do that, but from 2 to like n greater than 2, the transition there. So in n equal to 2, what we have done is essentially we have exhausted all possible cases, but from there to n greater than 2, it has to be a kind of inductive step. You cannot, I mean, do it by exhausting cases there. So there, I think we are close, but we are not done yet. So far, our focus has been on representations. K-theory, we have not looked at. And as I mentioned, I mean, ideally, one would like to show that this sister algebra and the one arrived at by Matase and Yankin, they are the same. And then you have both the worlds available to you, like the results that you can derive using their techniques and the results that you can derive by using these generators and relations. So that is another thing to look at, whether they do give us the same sister algebra. I mean, there's a high likelihood, but one has to prove that.
is it easy to say from your construction of these representations that some of these modules are finitely generated projective at least?
Some of the?
Is it easy to check that some of your representations are finitely generated projective?
I don't understand.
I didn't get.
So your representations are modules. Okay. If you know the collection of irreducible representation, you can ask what combinations of these irreducibles form finitely generated projective modules. Is it easy to see how to construct finitely generated projective modules? Your representations?
No. I think no. We are looking at Hilbert space representations, and what you are referring to is perhaps what will come up if one wants to look at case theory and all, right?
Yeah, it's the first step to K-theory, but having modules, I could form some combination of these irreducibles, and then I can ask the question whether this combination is a finitely generated projective module. To start even think about K-theory, K0 at least. Sometimes, if you know your representation of your algebra well, sometimes it's possible to say which modules are finitely generated projective. But so I wonder how is it in your situation? Because your description of this representation is very, very concrete. So maybe K-theory is too ambitious at the moment, but at least determining these finitely generated projective modules would be easier.
Somehow, Tomek, you are assuming that, you are just saying that, since irreducibles are finite dimensional, you expect that these modules are just finitely generated.
Some combinations of them. So it's a basis for computation. So I wonder what can be get from this simple presentation of these irreducible modules.
Well, I don't know how much it is related. Sure. But this is a very important and deep fact proven by Makoto Yamashita and Kennedy KUMAR, which was at the heart of our Peter-Galois theorem, that whenever you have a free action of a compact quantum group on a unital sister algebra, and when you take an irreducible representation of this compact quantum group, but you form an associated module, then it's finitely generated projective. If this is a very difficult theorem. But it's true, always, in full generality. So I'm just wondering whether one could try to phrase your question in a form that would involve this result or would be able to take advantage of this results. But I cannot do it offhand.
But is there some natural action of some, at least quantum group here?
I mean, quantum group acts on itself, but then no, this is somehow, this is, it's probably, I told you, I'm just thinking aloud. It's because you're now talking modules about your group. So then group would have to be a base space. So this is no, that's not exactly a question. But surely what I'm saying is related. Okay, it's because again you have irreducibles and you form these associated modules, and then they are indeed finely projective. But you're asking a different question, because you are looking at finely projective modules over your quantum group C-star algebra. Because over there, the finely projective over the fixed point C-star subalgebra. So yeah, that's a bit sort of orthogonal story, but I would like to emphasize this is a very difficult theorem. It's an absolutely beautiful result of Makoto and Kenny. Okay, anybody else? You guys, any questions? No, no more questions from Warsaw. Anybody else on Zoom? I don't see any raised hands. Well, actually, there is one more question from Warsaw for me. I'm just wondering how different these crystal limit C-star algebras are from the C-star algebras of which you take the limit.
I mean, SQT, of course, we know that they're isomorphic, in fact.
Yes, exactly.
Here we don't know yet.
You don't know. Okay.
No, not yet.
But inside this SQT,
but that would be one interesting thing to look at. Yes.
Okay. I mean, it's related to Tomek's question about K theory, because if they happen to be the same, you know, everything, I suppose. My other question is the following: inside these SUQN C-star algebras, you have Waxman-Zeubelmann quantum odd sphere C-star algebras. Do you know how these crystal limits look like of these C-star subalgebras, and are they then, you know?
No, I think odd-dimensional spheres, it would be easier. It would be
exactly like because it's much smaller.
SUQ2 case, yes. In fact, I think there. I have to check, and but I think the crystal limit there would be isomorphic, in fact, to the non-zero Q cases.
Which would agree with the fact we know that they are graph C-star algebras, okay? And graph C-star algebras are very, you know, crystal-like. But as Tomek knows very well by now, proving that Waxman-Zeubelmann quantum spheres C-star algebras are isomorphic to graph C-star algebras is an extremely difficult task. So that's not an easy observation. It's quite a theorem, actually. Okay, good. So if there are no further questions, let us ask our speaker again. Thank you so much. I fully concur with Eric that this was a beautiful talk. I enjoyed it. I enjoyed it very much. So let me stop recording. Where do I have my button to stop recording?